In Chapter 4, we're going to apply the principles of bonding, shape, and reactivity that we discussed in Chapters 1 through 3 to our first family of organic compounds, which are the alkanes. Now, because alkanes have no functional group, they are much less reactive than other organic compounds. And so, because of this, a lot of this chapter is really dedicated to learning how to name and draw them, as well as what happens when rotation occurs around their carbon-carbon single bond. Now, many alkanes occur in nature, primarily in natural gas and petroleum. Natural gas is composed largely of methane with lesser amounts of ethane, propane, and butane. Methane in the atmosphere comes from both natural and man-made sources. And so petroleum is just really a complex mixture of compounds, most of which are hydrocarbons containing 1 to 40 carbon atoms. And petroleum compounds, like if you look at a barrel of crude oil, you can see that for every barrel, kind of what it's used for, but it's also used for starting materials for chemical synthesis. And these are all the products that are made from petroleum, including a lot of your plastics. So it's just really kind of interesting, I think, to see all the things that alkanes can do. Now, I want you to remember that alkanes are aliphatic hydrocarbons, and they only have carbon-carbon and carbon-hydrogen single bonds. Now, because their carbon atoms can be joined together in long chains or rings, they can be categorized as acyclic, which is one word, right? Or cyclic, okay, which means they form a ring. Now, acyclic alkanes have the molecular formula of CnH2n plus 2. And that N is the number of carbons. So, for example, if we look here at carbon 11, and then we say great, we come here, we say 2 times 11 plus 2, that's where we get that 24 from. So, acyclic alkanes are also called saturated hydrocarbons because they have the maximum number of hydrogen atoms per carbon. Okay, if we were to have a double bond, it would replace 2 of these hydrogen atoms. If we have a ring, because 2 of these carbons join together, we also lose 2 hydrogen atoms here. So when you look at cycloalkanes, right, or alkanes that are cyclic, these have the general formula CnH2n, right, because they have 2 fewer hydrogen atoms than that acyclic alkane with the same number of carbons. Now, I want you to remember that all carbon atoms in an alkane are surrounded by 4 groups, making them sp3 hybridized and tetrahedral. So all carbon atoms in an alkane are sp3 hybridized and tetrahedral. They also have bond angles of 109.5 degrees. You're going to see some different representations. We have a 3D representation shown here, where, remember, this is going back and this is going forward towards you. And then we also have a what's called a ball and stick model. And so you can see the ball and stick model. And that's hopefully to help you visualize that in 3D. You can also build this model with one of your model kits. Now, when we think about this, these are to help us visualize in 3D. And I want you to remember that Lewis structures aren't meant to imply any 3D arrangement. They're a two-dimensional flat representation. And so it helps us, if we can think about these organic molecules in 3 dimensions, because that's the space they take up in reality. So the simplest alkanes that we have are methane, which is shown here, and ethane, which is shown here. And you can look at their structures here and here. Now, let's talk about propane for a second. So we have propane. It has the chemical formula of C3H8, and here's a stick structure, a skeletal structure of it. And then we have the 3D drawings here. And what you notice here is that each carbon has 2 bonds in the plane, which are solid lines, right? And 1 bond in front, which is on a wedge. And then 1 bond behind that plane, right, which is on that dashed line, okay? And so this helps us visualize, hey, look, these solid lines are coming forward, right? And these guys are going backwards. And then these carbons are sitting right here in the plane of the paper or the computer screen, okay? And so we can see where, for example, that's in the plane right there. And then the wedges there are coming towards us, and then these here are going back, okay? And so that's how we need to visualize this. If you have a great imagination, organic chemistry is for you, right? Because we're going to visualize these and eventually we're going to rotate them. If you're interested in dental school, this is really helpful for practicing visualizing things in 3D, including eventually tooth structures, right? So let's talk for a second about constitutional isomers. Now, we have mentioned these before, right? So I just kind of want to refresh and review. And this is where you can have a molecule with the same chemical formula but a different arrangement in space, okay? So these guys have the same chemical formula, but a different arrangement in space, okay? So when we look at this, a really good example is butane, okay? There are 2 different ways to arrange 4 carbons with all single bonds with the same formula that is C4H10, okay? So this is the same arrangement. These names are butane, and then we are going to learn how to name in the next screencast 2-methylpropane or isobutane, and isobutane is just the common name, okay? And so these, when we look at this, right, I want you to notice that we use the term straight chain alkane for when we have a straight chain like this, and then we use the name branch chain alkane for when we don't have a straight chain alkane, when there is a branch off of it. Kind of like if you think about a tree, those are the branches in the tree. I want to say a few other things about constitutional isomers. These are also known as structural isomers, and we are going to run into other types of isomers later, and so that's why we're making this distinction. And these, again, just differ in the way atoms are connected to each other. Okay? So, when we draw molecules, or when we draw these alkanes, it's important to understand that when we look at C5H12, when we look at pentane shown here, if it's arranged this way, it's still pentane. There are 5 carbons in a row. If it's arranged this way, it's still pentane. Those are 5 carbons in a row. 1, 2, 3, 4, 5. If it's arranged this way, it's still 5 carbons in a row. 1, 2, 3, 4, 5. So we can draw these in a lot of different shapes and it still be pentane because we're using a 2-dimensional surface to represent something that's 3-dimensional. So if you draw it like this and your neighbor draws it like this and your other friend draws it like this, you all are correct even though they look different. Okay. Now, pentane is the name when we have 5 carbons. If you look here, this is a summary table of straight chain alkanes. And I want you to look at the suffix. So the suffix, which is ANE, identifies the molecule as an alkane. Okay? And so when we look at this, it's these prefixes that are shown here, right, are based on the number of carbon atoms. If you have 1 carbon, the prefix is meth. The ANE here is based on the suffix. So all of these are going to have the same suffix because, and that tells us these are all those straight chain alkanes, right? But then what we're going to see is they're going to have different prefixes based on the number of carbons. So the prefixes, and so you just really have to commit these to memory, okay? So the prefix meth means 1, F, I'm going to use blue here, I think. F means 2, prop means 3, bute means 4, pent means 5. So I think about a pentagram, right? That's got 5 sides. Hex means 6. I think about a hexagon, right? There's 6 sides. Hept means 7. 8 means 8. I think about an octopus. 9 is known. 10 is deck. And then past 10, we start putting prefixes on the deck. So 11 is undeck, and then we have dodeck, and then trideck, and then tetradeck, and then pentadeck. And then when you get to 20, it's icoso right there. I want you to notice here, as we increase the number of carbons, the number of constitutional isomers increases dramatically because there are just different ways that we can represent these in 3 dimensions. Now, this is important because these different isomers have different properties, like boiling point. And so we'll talk about that later. Now, I also mentioned kind of at the beginning that these alkanes can form rings, and so those are called cycloalkanes. And remember, these just have the molecular formula of CnH2n, right, and contain carbon atoms in a ring. When we look at this, most of the time you're going to see these drawn as the skeletal structures here. When we name these simple cycloalkanes are named by adding the prefix cyclo to the name of the acyclic alkane having the same number of carbons. Right? So for example, there are 3 carbons here. If you were a 3-carbon straight chain, it would be propane, and so now we're cyclopropane. Butane, 4 carbons here, now we're cyclobutane. And so that's how we differentiate the straight chains from the cyclic compounds, is by using that prefix cyclo. In the next screencast, we are going to talk about how to name your alkanes. Yay!